Okay, so here we go. We're on section 6.4, the fundamental theorem of calculus. And this is the connection that we want, the shortcut for evaluating areas, which are our definite integrals. And in section 6.1, we did an integral of a function, and we called that the antiderivative. And then we took a turn in left field. We took a turn in left field in section 6.2, and we randomly started talking about areas. And I made you do areas of these sums. We had these Riemann sums in which I went from 1 to n, and we did the limit as n goes to infinity, and we had a lot of arithmetic that we had to take care of, and these formulas that you didn't have to memorize, but you had to use all the time. And one problem took a half a page. And then in 6.3 we called those areas, we called them Riemann sums, and we used this definite integral notation, and that meant the area from A to B between f and the x-axis, and that's what that area was. And so now it's no coincidence that we used an integral sign when we talked about area, and we used an integral sign in section 6.1 when we talked about the antiderivative. When you want to compute the area between a function and the x-axis, between two x values a and b, the way that you do that is you compute the antiderivative. And then you simply plug in the two endpoints, b and a, the upper one, b in first, and then the lower one, a in second, and then you subtract. So I have three examples here. On number 1 here, 1 to 3, x to the negative 2 dx. To find the area, we're going to do the antiderivative, which remember requires the reversed power rule, or the power rule for antiderivatives. So you add 1, negative 2 plus 1 is negative 1, and you divide by that. Now you're going to want to plug 1 and 3 in and subtract. So we don't have a plus c, by the way. We don't have to do plus c. This is not an antiderivative function answer. This is an antiderivative simply to compute an area. And so you don't need plus c. It would end up subtracting out anyway. So we just do 1 to 3. And this notation right here, where I did this vertical bar, this is called an evaluate bar. And what that means to do is to evaluate this function at both of these numbers. That just means to plug both of those numbers in and then subtract. So when I plug 3 in, 1 over negative 1 is negative 1. I have 3 to the negative 1, or 1/3. Minus, now if I plug 1 in, I have negative 1 times 1. And so I have negative 1/3 plus 1, and the answer here is 2/3. Okay, I'm going to change this next example. Let's just do the integral from 0 to 3 of x squared plus 1. This is an example of a question that I would have asked you on the quiz, in which you had to compute the area by the limits of the Riemann sums. Okay, so you're going to do your antiderivative, 1/3 x cubed plus x, normally plus c, but we don't need that here when we have bounds. So instead of doing the plus c, you're going to plug in 0, 3 and 0 in, and subtract. So when I plug 3 in, I have 1/3 times 3 cubed plus 3. When I plug 0 in, I have 1/3 times 0 cubed plus 0. And then you're going to subtract those two answers. And that's the area, and it's as simple as that. So this is going to be 12. This 1/3 times 3 cubed is 9. 9 plus 3 is 12. And then all of this is, of course, 0. Okay, and then let's do this third example here. Pi to 2 pi of the sine of pi d theta. And I'm going to show you this one in a couple of different ways, because we're going to compute it doing our antiderivative. So this is number 3. But this finds, if you graph your sine function, sine of 0 is 0. So pi is here, this is 0 0, and this is 2 pi. So this is going to find how much area is right there. And we know from the last section that area below the x-axis, the integral will compute as negative. So I already know my answer should be negative. All right, so let's do this using antiderivatives. Whose derivative is the sine of theta? That would be sort of cosine of theta, but the derivative of cosine is negative sine. So we must have started with a negative cosine if we got a positive sine as the antiderivative, or as the derivative. So negative cosine of theta is my antiderivative. I'm going to plug in pi and 2 pi and subtract. So I get negative cosine of 2 pi minus negative cosine of pi. Minus and negative is a positive. The cosine of 2 pi is 1. And the cosine of pi is negative 1. And so my area is negative 2. So this area right here in the sine curve between pi and 2 pi is negative 2. Negative because it's below the x-axis, but the shape itself will have an area of 2. Okay. On this question, I have a couple of functions, if you look at these. And I want to find the area of the region that's bounded by the functions. So I'm going to start this off with a picture. I'm going to graph these. And so when I graph this, the x cubed plus x, I'm just going to factor out an x. That's x times x squared plus 1. So that equals 0 at x equals 0. And then it's just a cubic. What would happen at 1? At 1, I would get 2. And at 2, I would get something really big. What would I get at negative 1? At negative 1, I would get negative 1 minus 1. I would get negative 2. What am I? I'm doing x equals 2, y equals 0. Let's find out what happens at 2. At 2, I get 8 plus 2, which is 10. Okay. So there's my x cubed plus x graph. X equals 2 is this vertical line. So this is the line x equals 2. This is the line y equals x to the third plus x. And the line y equals 0 is right here. Okay, so can you see the region that they mean for us to find the area of? The region has to be bound, have boundaries that are formed by those curves. And so if I call it the region R, I'm talking about this region here. And it's not a shape. It looks somewhat triangular, but it's not a triangle because this is a curve, right? Not a straight line like in triangles. And so how do I find the area of that region? Well, notice it's between a curve and the x-axis, starting when x is 0 and ending when x is this number here, 2. And so that area is an integral. So I want to integrate x cubed plus x between 0 and 2. That gives me the area. And now you know the shortcut for this. This takes no time at all. We do our antiderivative. No plus c necessary because I'm finding an area. I plug the upper bound and the lower bound in. With the upper bound, I get 4 plus 2. And the lower bound, I get 0. And so my area is 6. So much faster. Okay, so that's the fundamental theorem of calculus. That's actually part 2 of the fundamental theorem of calculus. With that, we're going to talk about another topic here really quickly. We're going to talk about the average value of a function. So let's talk about what an average is. What is an average? Well, let's say you have test scores, and let's say you have 4 tests, and the scores on your 4 tests are 90, 88, maybe you bombed one, a 70, and a 92. So let's say these are 4 tests that you took. You can find the average score. You can find your average test score. The way you would do that is you would add up your test scores, and then you would divide that by 4. And this averages to an 85 if you add these up and divide by 4. Okay, so let's extend this idea. We're going to find the average y value of a function in an interval. So the picture, the idea here is let's just talk about x squared. So let's say this is y equals x squared. And let's talk about y equals x squared on the interval 0 to 3. So at 0, I get 0, 1, I get 1. At 2, I get 4. And at 3, I go all the way up to 9, right? And so what I want to know is if you look at these y values, the y values range in number between 0 and 9. But on average, what is the y value? Like, what y value are we at most often? So you might think maybe it's 4.5. Maybe the average y value is 4.5 because 4.5 is the exact middle of 0 to 9. But that's not what the average y value is of x squared, because what happens with x squared is that you spend between 0 and 1, you're just at 1. And if this were drawn to scale, it would be a little bit better. But then from 1 to 3, well, 2, at 2 you get 4, but you jump in just a width of 1, you jump a height of 5. And so between this small amount of width of x, you go really far up in y. And so you spend more time below 4.5 than you do above 4.5. So that average is going to bring you down below 4.5. Okay, but to actually compute an average value, it's the idea that we just said. You're going to add up all of your y values. And that's actually what an integral does. It adds up all of your y values. And then you divide that, because 1 divided by, it divides. You divide by the whole width of the interval. And so if I want to do the average value of f of x equals x squared on the interval 0 to 3, then using this definition, I would say that f average is 1 over 3 minus 0, integral 0 to 3 of x squared. So that is 1/3 integral 0 to 3 x squared. Now I know how to do this integral, this definite integral. It's an area. I compute the antiderivative. I plug in the two values at the ends, the upper and the lower bound. So for the upper bound, I would get 3 cubed, 1/3 of 3 cubed, and 1/3 of 0 cubed for the lower bound. So this is 9. And so I do 1/3 times that. And so 1/3 times 9 is 3. So my average y value is 3. Notice that 3 is below 4.5, which is what we kind of thought it would be, because I spend more time below 4.5 than I do above 4.5 because of the nature of the curve. Another thing that means is if you look at this integral, or if you look at this definition here, if you take the average y value, the average value of f, and you multiply that by b minus a, you get the area, a to b, f of x dx. And what that tells us is that in this specific example, if I look at 3, which is somewhere here, here's 3, y equals 3. If I find the area of this rectangle, which is 3 by 3, which is 9, that's actually the area from 0 to 3 of under x squared. And so the blue rectangle has the same area as the green shaded region. And so that's just the definition. And here's an example that you all can do on your own using that definition. I'm going to move on. There's actually a second part of the fundamental theorem of calculus. The second part of the fundamental theorem of calculus. And the second part of the fundamental theorem of calculus goes a little bit backwards. When we did the area, and we said it's the same thing as the antiderivative, then that means we should know a new derivative. Because if you know that the area gives you the antiderivative, then that means the derivative of the antiderivative should have been the original. And that's what the fundamental theorem of calculus part 2 says. It's talking about the fact that an integral is the inverse or the opposite operation of a derivative as a derivative. And so this is our definition. This function is strange. This is a new function. You have never seen this function before because you have never had integrals before. But this new function I like to call the area function. It computes area. the way that g of x is defined is it says start at some number, and it actually doesn't even matter what number you start at. And the variable is b. The end point of the area that you're finding is the variable. And so what it's asking you to do is say, okay, so what's the area up until this spot? What's the area under f up until, this x value? What's the area up until this x value? And you vary x, and it tells you different areas. Now, if I take the derivative of this brand new area function, then the derivative of this brand new area function is the function you took the area under, because they're opposites. And so the fundamental theorem of calculus part 2 is going to feel kind of strange, but it is essentially just a derivative formula. And the derivative formula tells us that the derivative of the integral is the original. Okay, and then there are a lot of things specific that you have to keep in mind. One is that this has to be a number. You have to start with a bottom number constant. Doesn't matter what the constant is, but it has to be a number. Like you can use 7, or you can use pi, you can use -411. But whatever this a is, it has to be a number. And then the top is a variable of x. Okay. Now, there's a chain rule form of this, because once you learn a derivative, you have to use the chain rule on that new formula. And so the chain rule would tell you, well, what if this isn't just x? What if it's x squared? Then the derivative would be the original, but with an x squared there, and then times 2x, because this is your inside. Whenever we talked about the chain rule, we said it's the derivative of the outside, keep the inside the same, multiply by the derivative of the inside. So this b upper bound is your inside. All right, let's do some examples of this, and then we will be finished. So this says use the second fundamental theorem of calculus to find f prime of x. And notice we're using capital F of x as the name of the area function. And of course we should use capital F of x. It's equal to an area, which is an integral, which is an antiderivative. And we like to use the letter capital F for antiderivatives. And so I'm just going to use the formula here, which says that the derivative of the antiderivative is just the original. So the answer here is just square root of x to the 5th minus 2x plus e to the x. So the other thing that gets confusing for people about this is the fact that you have to use t's in here. And then the x is the upper bound, because this actually isn't the variable that the area is concerned about. That's another variable. And that's it. That's all it is. It's telling you that if you do the derivative of the integral, you just have the inside. Okay, so here's example number 2. In example number 2, let me zoom this in a little bit. In example number 2, this is a little bit different, because look what's happening. Look what's happening here. The x is on the bottom. The formula doesn't work if the x is on the bottom. So what you have to do is rewrite the question so the x is on the top. And we learned about this last time. You can reverse this as long as you negate. So you can flip your upper and lower bounds as long as you get, but that means you get the negative integral. Your integral is the same area but negated. And so all I've done here is rewritten the question, but I flipped the a and b, which means I added a negative. And that's one of those properties of integrals. Now I'm going to do the derivative, because now my formula will work. Notice this is a constant multiple, negative. So I get negative whatever the derivative of this part is, and that's that new formula. So it's just 3x squared minus 4x plus cosine squared of x. And I should be careful to distribute that negative. Notice there's no plus c, right? Because a plus c is an antiderivative. And what am I doing? I'm starting with a function and finding its derivative. So it's the opposite operation. I'm not doing an antiderivative. I'm doing the derivative of the antiderivative, which is why the answer looks just like the question, because they're reverses. Okay, so on this third example, I have a chain rule. The third example, I have a chain rule. I want to point out the issue here. This is an x squared. It's not just an x, it's an x squared. And this is my inside. This is the inside, this is the u. And that is what I use the chain rule on. And so when I find my derivative, f prime of x, I'm going to do what the formula says, which is whenever you have x up here, the derivative is the original, but with x plugged in. So I wouldn't have put t cubed, I should put x cubed. But I don't have an x up there, I have an x squared. So it's 1 over x squared cubed, because whatever was up here is what gets plugged into t. Then because I have chain rule, I multiply by the derivative of the top. And so this is 2x over x to the 6th, which would reduce again, but let's just leave it there. So that's the chain rule form. And then my last example is the most complicated example for fundamental theorem of calculus, and it's a classic example. So there are a couple of things going on with this example. First of all, we've got chain rules, so we're going to have to take care of that. But secondly, and more importantly, my lower bound has x's and my upper bound has x's. And the formula only works for the upper bound to have x's. So how do we do this? Well, we have to rewrite the question again. And the way that we rewrite the question is we use additivity. Additivity was the rule that said if I go from A to B, that's the same as going from A to C plus C to B. You can stop anywhere. So I'm going to stop at 0. I'm going to rewrite this as two integrals, as two areas. I'm going to go from sine of x to 0, and then from 0 to x squared. Now I can do the derivative, well, I can do the derivative of this part because it's in the right form. I have to do one more thing to over here. I have to have the x's as the as the upper bound, not the lower bound. So I'm going to reverse those and negate, just like I did it on the second example. Oops, I forgot my sine of x. Okay, and now I want you to compute the derivatives of these, and be careful because each one has a chain rule. Each one has a chain rule. And so when you do this, I'll go ahead and help you on this. So let's do our derivative. So we have negative. So I have to do the derivative of the integral, which means nothing. I don't do anything. My answer is still tangent over t squared plus 2. The only thing is that I'm doing the tangent now of whatever was up there. So it's the tangent of the sine of x over the sine of x squared plus 2. And so it's the t. The t gets changed into whatever was my upper bound. Then I have to do the chain rule. Sine of x has a derivative. It is cosine of x. So that's the derivative of this first part that I've boxed. Plus, now the derivative of the second part, I'm going to plug in x squared. So I have tangent of x squared over x squared squared, which is x to the 4th, plus 2. Do the chain rule and multiply by the derivative of x squared. And then we're all done. Okay, finished.